Good afternoon. My name is Dave Folsom. I'm with Pearl TV, and I do much of the engineering that is being done for the Phoenix Pearl Phoenix project for ATSC 3 model market station. And as we'll see in this presentation that I'm going to give, not only we have a model station on, but we're working with other broadcasters to bring other stations on, at least one other station on in the Phoenix market, including an SFN. So we're going to have a chance to go over a little of how we got to where we are and what the challenges have been and how we've gotten past them, and also maybe get to a point where we can answer some questions for you, because we've had some pretty good experiences over the last year of what seems to work and what doesn't, and I think I'd love to be able to share that with you. Pearl and the Phoenix market partners are shown, and I won't list them all, but Pearl itself is a group of like-minded broadcasters that are group owners of television stations throughout the United States. There's 8 companies in all. But in addition, in Phoenix, we were able to have the Fox Television station group join us, as well as NBCU, PBS station, and also Univision. And that went a long way to creating a coalition that made the model market possible. The list of the folks are up on the board. The whole point of starting a model market was to provide a means by which we could develop a commercial television service, because it's one thing to have the technical standard, but it's a second thing to have the mechanics of making sure that we could implement business plans to make it practical. It isn't really designed just to be a replication of current ATSC1 services. We have to be able to adapt the system to be able to do other things, or why bother? We wanted to, right at the beginning, to make sure that it was an open test bed, that we would be able to carry and replicate our basic television service that we carry now, and that's a mandate from the FCC and the report and order in November of 2017. That was a requirement. We also wanted to make sure that the consumer propositions were also investigated to ensure that the expectations of what the consumers wanted were reflected in what the capabilities were. We wanted to make sure that we also have content protection built into the system. It is part of the standard, but implementation of that is another matter. It requires the confidence and the cooperation of the rights holders, and that would be the networks and the studios. And we wanted to be able to not only try that out, but also provide a model to them to show that their content would be protected. And we also wanted to make sure that we looked at all of the business opportunities that might also be out there in ATSC 3. I think if you were here for the announcement of the 40 markets that we'll be rolling out over the next couple of years, there was a lot discussed about other business possibilities in using the transmission as a platform for delivering other than video and audio. When we first thought about this, which was just over a year ago, it's a year ago in December, last December, and before we even thought about having the model market, we wanted to make sure that we looked at what the basic consumer service should be. All the way from signal protection, which is a key, as I mentioned, making sure that we had audience measurement built into the system, that MVPDs were included, because as broadcasters, we want to protect our retransmission revenues, and we don't want to do anything that would hurt current business models. We also want to make sure that the modern applications could be provided or adapted for use on air, and that would be most specifically web type services for deep guides and bring deep content to the audience. And also one of the use cases that was discussed this morning in this morning's presentation was the mobile use case, and there are all kinds of possibilities from delivery of software to individual automobiles, to downloading entertainment content, updates to the services that are inside the vehicle, like maps or whatever. But because of the robustness of the ATSC3 signal, it provides a one-to-many platform that it's very, very solid and covers a wide area, which is really what the automobile manufacturers are interested in, at a relatively low cost compared to other wireless delivery methods. We wanted to make sure that we had some proofs of concept. We wanted to be able to not only implement these things, but to, after we had a concept, that we had an ability to be able to show that these concepts would work. And whether it was digital rights management, adjustable advertising, and on down the list, as you can see, each one of those were major concepts that we wanted to be able to, over a period, as the equipment became available, the broadcasting equipment became available, be able to implement and show to the industry that these ideas did work and that they were practical. And if they were practical, in what form. Luckily, we got the support of an awful lot of companies. Because we made it a completely open platform for the industry. We've received tremendous support from all the major manufacturers of equipment that for getting the broadcast signal on the air. Too long a list to name here, but you can see from the logos that are up on that screen right now that they were solid supporters, including the consumer receiver industry. And that was important. It's one thing to be able to transmit the signal, but we have to make sure that the consumer receiver industry is also supportive and will be providing receivers. And in that specific case, you'll notice the logos for LG, Samsung, and Sony are up there as well. They have provided test receivers and prototypes for us to ensure that the signal works over a wide range of manufacturers. And we have more than one broadcast chain. Even though we have a single channel on the air, we can swap equipment out to see how it mixes and matches together, and ensure that we have as compliant a stream as possible. Univision provided the facilities for us. We wanted to make sure that we had a signal that was relatively representative of the market. It's kind of an eye chart up there, but what you're looking at is the stylized coverage area of the FCC coverage area in the outside circle. And inside of that, and again, it's difficult for you to see, but the purple portion is, believe it or not, over 40 dB of receiver margin. So in the Valley of Phoenix, even though this is a 15 kilowatt station, we have a tremendous receiver margin there in ATSC1, and we have actually better margin than that in ATSC3, about 3 or 4 dB better. So it was an excellent market as a test, kind of devoid of some of the interference and other issues that you have in other markets, so we can really have a flat plane to compare with other markets and other installations at a later date. If we always had to make excuses in the market because, well, it would have worked better, but we had that mountain in the way, or we have interference from that adjacent market, that would not make for a good story. Okay, how did we make it work? Because we weren't given extra spectrum. What we first had to do is be able to take the signals that are currently, the ATSC1 signals that are currently on the primary station, which was KFPH, that's the call letters of the station in Phoenix, and we had to move those ATSC1 signals off, those services off to 3 other stations. One to carry the primary HD signal, and 2 other multicast signals. The primary signal went off to KTVW, as you can see in the on the display, and that happens to be the sister station of the station, so that was an easy one. When you have a duopoly or a co-owned station in a market, if you have the ability to be able to work with a partner that you know very well, maybe even in the same facility, that makes it particularly easy. And the multicast that came from the ATSC 1 signal went over to the Tegna and Scripps stations. We provide them over the over a fiber connectivity, and there was enough bandwidth left in each of those stations to be able to take the ATSC 1 signal. So with the fatter arrow, you'll see that allowed KFPH to now be free, all of its bandwidth be open and available for ATSC 3 transmission. Okay, one thing that, one important matter in ATSC 3 is that it makes use of Hev C encoding, which is our H.265 encoding, which is far, far more efficient than the MPEG-2 encoding that we're using now. And as a result, we can carry a tremendous number of individual services on that one transmission. Realistically, carrying 1080p signals at 60 hertz, we can carry about 5, possibly 6 in a statistical multiplex, but 5 comfortably. So that means that we can essentially provide ATSC 3 capability to 5 stations on a single channel, assuming equivalent service. And 1080p is actually better service than 1080i or 720p. So that is an upgrade. But you know, ultimately, these individual stations, after they're on Lighthouse for a while and the population of receives more and more ATSC 3 receivers, there'll be a point at which that station would flash cut, and those stations would then move over to another Lighthouse until finally it migrates down to all stations flash cutting. But this shows a methodology to get the first Lighthouse working in a market and taking care of quite a few of the stations at one time. Additionally, we've been able to have up to 1 4K signal and 2 or 3 1080p's on the air at the same time. So you can carry 4K. A couple of 4Ks and a 1080p is very possible. There's sufficient bandwidth for that. And those are all at a modulation encoding methodology that's equivalent to the coverage that we now have in ATSC 1. Now, if you wanted to go and have less coverage, you can have much more bandwidth and carry even more signals. But for now, we wanted to be able to show equivalent coverage to ATSC 1 and to show the industry how many more signals we could carry. This is a very, very simplified version of what's required to get a ATSC 3 transmission on the air. On the left-hand side of the block diagram is input conditioning. You clearly, at first, are required by the FCC to simulcast the signal from your ATSC 1. So either you'll provide the signal from your studio to the Lighthouse station via fiber or via cable, or it may be from the next room, or conceivably off the air. But one way or another, you have to input condition that and decode it and create a component signal that you then can provide to the encoders. So why there's a number shown stacked up is because you may have 5 or 6 TV stations or services that'll be on that single channel. To the right of that, you'll notice there's a up-down cross converter. If you're going to be transmitting in 1080p and the input is 720p, you need to cross convert. So there has to be some kind of up-down cross conversion depending on how you're going to transmit the signal on the air. After the up-down cross conversion, which is all part of the same box actually, is encoding, Hev C encoding. That encoding can be variable bit rate or a constant bit rate. When we first got on the air in Phoenix, we were constant bit rate. And as the manufacturers were able to finally roll out Hev C encoders that were variable bit rate, we switched over quickly to that because they're far more efficient, and statistical multiplexing. And that allowed us to move from, let's say, 5 1080p signals on the air and services on the air to 6. The output of that then goes to a packager. Because it's dash, you need to put an MPD to tell the receiver what's going on with what's being delivered to it. and then it goes from dash into a route encapsulator. And the route encapsulator essentially turns it into a HTML signal. And what's actually delivered to the receiver is an HTML IP stream, which the receiver has in effect a web browser that decodes the signal and displays it. You don't see the normal accoutrement that goes along with a web browser on your home, but what's going on behind the scenes is HTML5, and what you're actually seeing on the screen is a decoded window inside that browser. Now that browser will come in handy later on, because you can use that browser capability, HTML capability, to provide applications to the screen, whether it be a contextual guide or a ability to control a TV set, or to find out more information like deep linking. All of that is possible through the browser that's in the receiver. And as you'll notice that above, in probably an eye chart above there, is a mention of applications. They're also put in right there. We're at the route encapsulator. The output of that goes to a scheduler. The scheduler is used for a lot of purposes, but the easiest one to explain is it breaks the signals into what you've decided your transmission modes would be, and you can transmit more than one mode at a time, so you can have a very robust, low bandwidth, high coverage area signal on one physical layer pipe, and you can have a more modest or less aggressive modulation encoding for, say, something that would replicate your current coverage. You can have up to 4 of those going on at one time, and possibility, I think, of 64 in all. But the reality of the matter is the receivers only have to support 4, so the 4 is the likely use. You can put audio on one PLP and have that with a more robust signal than the video, for example, or you can have them all on a single PLP, or you can have multiple services on a single physical layer pipe. The broadcaster has given a lot of, we've done both. We've had the ability, and we've actually transmitted signals simultaneously in 2 PLPs. We put the audio on one and the video on the other. We've done various combinations, and that comes in handy if, for example, where you want the coverage area of your audio maybe to be further and be more robust than the video. That's kind of goes back to the old days of NTSC, where the FM was more robust, where FM audio signal was more robust than the AM video signal. And oftentimes you could be able to hear the baseball game, but you couldn't see it. So that's left to the broadcaster to make that decision. Obviously from there it goes through an STL to the exciter and the transmitter. The transmitters are essentially the same transmitters you're using now for ATSC1, very little difference. And the exciters, the current exciters from most manufacturers are dual, can work in the ATSC1 mode or the ATSC3. It's just a matter of a software license generally. I think every one I've seen of all the recent brands are all dual. Here's a kind of a test timeline from starting up at the second quarter in 2018. And this is a general timeline just to give you a feeling without all of the super detail, but it shows you what we were doing at those particular times and what we are currently involved in now. We want to keep the testing going, because we're in a phase now, and particularly providing a lot of support for our receiver manufacturers to get compliant test streams as we try to communicate as best we can to the receiver manufacturers precisely what services likely the broadcaster will want. ATSC 3 is a huge menu of capabilities. And you have to, broadcasters won't be using all of those capabilities to begin with. And so we have to be realistic about what we really want to focus on to begin with. And that has to be done during the testing, making sure there's a business use case for these things, not asking for things that there aren't necessarily business use cases for, and make sure that those things work, and also provide those streams to their receiver manufacturers so that they can test them themselves and make sure that their designs will be able to decode or support whatever we have in mind. they've been very supportive, tremendously supportive of what we've done. Also, at the same time, we have a lot of work to do working with the cable industry, the MVPDs, and to ensure that they understand that, we're not pushing so hard with ATSC3 as a cable cutting mechanism, that we really want to work with the MVPDs to ensure that we have a means by which that we can support a lot of these capabilities in cable going forward. Now, whether it's possible in the current legacy cable systems, I'm not sure, but for sure in the newer systems, the IP-based systems, they're likely to be able to support a lot of the capabilities that we're going to have, whether it be UHD or high color gamut, wide color gamut, or there'll be a lot, or high dynamic range. There'll be a lot of capabilities that the IP-based MVPDs will be able to support on day one. And so there's a lot of discussions that are going on behind the scenes, not only on the technical side, but also on the business and use case side. We're also working with, going forward, with a number of auto manufacturers, because they're interested in, as I mentioned at the beginning of the presentation, about the possibilities of being able to deliver content of all types, from testing data to software upgrades to receivers inside the automobiles, to maps. There's a wide range of things that they'd like to be able to make use of. Their lead time for the automotive industry is almost 4 years. So things that we're testing out now will not see the automobile industry until the 2023 model year. So you can see, because of the long lead time, the testing has to come early to make sure that it gets used. One of the things we did last year is in August of last year, we had a Plugfest. We had 65 people that came from all of the industry, from receiver manufacturers to broadcast equipment manufacturers, the networks. Many of the networks were there as well. We had from 20 to 21 different companies, and we had a chance to go over a lot of the technical details that fall between the standards, if you will, that were so critical to make sure that this equipment all worked well together, that we have as much compliance as we could get, and to figure out what those problems were that we needed to work on. It was a week-long session, and it went extremely well. And it's amazing to get so many competitive companies together in the single room and to work to a common goal. And I thought it was a tremendous achievement for all those that participated in it, to be able to kind of put their corporate hats aside and think of the greater good of being able to get a new standard on the air successfully, to ensure compliance and ensure that there was a proper interconnectivity between their equipment, which was really critical. Some of the lessons that we've learned so far, the implementations are still not quite there. It's to be honest with you, most of this equipment has only been built for just over the past year, and so much of it is still a work in progress. The receiver manufacturers started out with probably the least capability to begin with. They started with the Korean implementation of ATSC3 that went on the air at the beginning of 2017, and they needed to adapt those for use in the United States or North American version of ATSC3. They did that fairly quickly and have been doing software updates all year, and I think they are very far along in their designs, which is great to see. With our equipment manufacturers, the broadcast equipment manufacturers, it's some are further along than others. They all understand what the issues are, and they're working very quickly. The good news is that all of this equipment is software derived and software driven, and it makes it easier. The turn cycles and improvements come quicker than if you have a hardware implementation that you have to modify. Switching to things that are probably most important, we're working also with DRM manufacturers, which is, there are a number of different companies that support DRM. We've selected, to begin with, Widevine, which is a Google company, as the first DRM, not the only DRM that will be supported, but we had to begin somewhere. And we're working with the networks and studio that, in a lot of cases, the networks are the studios, to ensure that the content protection that we're providing to the signal is what is acceptable to them. Because they made it clear right from the beginning when ATSC 3 first was discussed, because it was an IP-based service, they were concerned that there was a chance that their signals would, or their content would be compromised. It would be too easy to compromise and send it out over the internet, let's say, because it's IP-based. So they said right from the beginning that they wanted some form of content protection, at least as good as they have in over-the-top. And as you probably already know, all of the over-the-top providers all have content protection, be it Hulu or Netflix or Amazon Prime. So we're working with, right now, with Google or Widevine as our first provider to work through the issues. If the receiver is connected to the internet, it's a fairly easy thing to provide the DRM system and the keys that are required in the certification. It's a little more difficult when you have a single-ended receiver that is just over the air and has no connectivity to the internet to be able to get the cert that's required to allow the signal to be decoded. And so that's been the challenge, and Google's come up with a way of dealing with that, and we're working through that and doing the testing now in it. There's some other more esoteric things up on the list there. I'd be glad to answer any questions about it when we get to the question and answers, but I won't bore everybody with all the details. But we have learned some technical lessons for sure. Channel change time, it's mentioned there, is an important part of it. And one of the things that we're investigating is the use of CMAF. CMAF is a industry-wide, used in particularly the over-top industry right now, as a means to allow for quick capture of segmented streams. And because ATSC uses segmented streams, ATSC 3 uses segmented streams, we want to make sure if you have long segments, let's say 5 or 5 second long segments, we don't want to have the user wait 5 seconds after they change channels to have the signal come up. And there are ways around that, using chunking, and CMAF is a definition of how that chunking works that's pretty well accepted, particularly on the OTT side. On the long list here of things, I've mentioned the DRM. One of the things that has been interesting is I mentioned that all of this broadcast equipment is software based. So generally speaking, when you look at a rack full of equipment, it's all PCs or servers. And the servers inside have virtual images in them of the actual application, be it an encoder or be it a route encapsulator. They have a tendency, the manufacturers have a tendency to virtualize those in virtual engines. And it wasn't long before a couple of manufacturers said, well, gee, why don't we just put a very big server in there and we'll virtualize the whole broadcast chain, all the way from when the video comes in at the beginning to where it comes out of the scheduler at the end. And everything inside will just be a virtual engine, and there will be no particular specific pieces of hardware in between other than the server that this is all sitting on. Well, we have at least 2 manufacturers that are doing that. All of the manufacturers are virtualizing pieces of it, so they may have a scheduler and a route encapsulator together, or a packager and an encoder, or whatever. The issue we found there is that it becomes, when something decides to stop working, it becomes a problem to troubleshoot it, because there is no way of troubleshooting the software individually or swapping it out, other than swapping out whole virtual images. So that's been difficult for us. So one of the concerns that we have is with the manufacturers of the equipment is to find out a way in which we can have breakouts, so that we'll be able to troubleshoot it easier to see which of the virtual devices that are inside are the problem child. We've been working with the broadcast receiver manufacturers in terms of the size of the cache. They'll all provide some cache inside the receiver, and the amount of cache that's in that receiver will determine how many web pages that we can cache in there as you go from channel to channel. You don't want to have to pull up another web page each time. If you're always going back to the same channel, it would be nice if it was cached in there. Also, if we're going to push up other content to the receiver, that has to be stored somewhere in the receiver. So that's been an issue in terms of finding out what the optimal amount of cache is in the receiver. I think I've discussed it just about everything else here. I mentioned that we are doing statistical multiplexing. It's no shock that statistical multiplexing and variable bit rate is far more efficient than constant bit rate. And we went the first half of the year in testing only with constant bit rate, and that was difficult to try to get a lot of streams on the air at the same time. We don't have that problem at the moment now. Okay, looking forward. One of the things that came out of this year is to create a launch service profile. And that launch service profile was critical for the receiver manufacturers to know. I mentioned earlier on in the presentation that we needed to know what the requirements of the receivers were going to be. Again, we have a wide capabilities, but not all of those capabilities are necessary at the beginning of the service. And so we had to define that and bring that down to a document that we could provide to each of the receiver manufacturers that would say, yes, we're interested in these mod cards, yes, we were interested in this capability or that, and actually define it in actual language and in specifics of numbers when the numbers were required. That document has been provided to the receiver manufacturers, and we've debated it, because we have a tendency to ask for this, and maybe the capability is only that, but it provided a means by which we could communicate with the receiver manufacturers about exactly what the broadcaster's expectations were. I mentioned Drm Signal Protection, that's a requirement. We're going to put a second lighthouse on the air in Phoenix. It'll be KASW. It's mentioned on one of the panels here, talking about SFN. We will not only have that second lighthouse on, but it'll also have a single frequency network with 4 total nodes, so that we'll be able to have 2 stations in the same market, one with an SFN, one without. We're creating a common framework. I mentioned that the receiver is displaying via an HTML browser, and we believe, as broadcasters, representing broadcasters, we believe that if we can work from a common framework, that helps the viewer understand what they're looking at. When they call up a station, if the menus that are seen around the screen that's pushed down as an application are different in one station than they are in the other, it gets confusing. It doesn't mean that they can't be skinned differently or the words can be different, but common capability should be in common locations on the screen. And so we're developing a common framework. Part of that common framework includes the digital rights management and how that's managed, and how it interfaces with the viewer. Also, selection of capabilities within the stream are also done by that. We'll be working, obviously, getting the word out through marketing and messaging to the industry. And MVPD testing is really going to be critical coming up this year. I mentioned that they're an important part of the broadcast ecosystem. They provide a tremendous amount of revenue to broadcasting, so we really need to make sure that we have them as part of in one of our partners. I kind of went through that quickly. I'm here to answer any questions you have. We have about a little while. We can answer some questions if you have any. What's that? Yeah, here's an interesting, yes, there is not a standard yet, and I'll explain. Statistical multiplexing works most efficiently when the statistical multiplexer can talk to the encoder. So generally you have a target range of bandwidth that you have, and you try to use as much of that target as you can, unless the pool, the amount of total bandwidth available, starts getting, you start running out of bandwidth. And so then there has to be a negotiation between the encoders about who gets what. That return path is really critical for statistical multiplexing to work as efficiently as it does. If the encoders are kept off-site, meaning wherever the transmission is being done from, if the encoders are at individual stations and then it all comes back to a common place, to a common statistical multiplexer, there has to be a return path to tell the encoders, gee, we're running out of bandwidth, you have to cut back a little bit. There's latency in that transmission, and too much latency at the moment, and there is not enough standardization about that. So we're working with the manufacturers about trying to deal with that and how to solve it. But for the moment, we recommend that the statistical multiplexers and the encoding be done in the same building. It's the only practical way at the moment to do it, and still have fast response. And you know, scenes change very quickly, and bandwidth requirements change very quickly. You cannot have any latency in that for it to work efficiently. So hopefully I've answered any other questions? I'll just mention that the Phoenix project is continuing. I mentioned we're putting a second one on the air in Phoenix. We'll be doing more testing. We're inviting people in to see the facilities when we can. As more receivers become available, we'll have the ability to show people at different locations in the area. We have a fairly small number of receivers right at the moment, pre-production prototype receivers. But that will go a long way, and we're working particularly with our industry members in testing their equipment as whether they are making antennas or receivers or transmission equipment or transmitters. We try to be an open test bed to just about everybody that needs our facilities. We don't have any really requirements other than to come down and join in with us. Any other questions? Thank you very much. Appreciate it.